14 students, sign-up sheets for basically our friend in the back who's already on our sign-up sheet, and I think that's it. So without further ado, let us welcome Dr. Maggie Makar, a presidential postdoctoral fellow here at the University of Michigan and a visiting researcher at Microsoft Research. Dr. Makar received her Ph.D. in computer science at MIT. While there, she interned at Microsoft Research and Google Brain. Prior to MIT, Maggie worked at Brigham and Women's Hospital studying end-of-life care. Her work has appeared in ICML, AAAI, JSM, the Journal of the American Medical Association. I think it's cool that you spelt out what JAMA stands for, but not ICML.
You never know.
It's just a totally different audience. Some folks are like, why did you spell that one? Some don't know what ASM. Anyway, JAMA, Health Affairs, Epidemiology, among others. And she received a Bachelor of Science in Math and Economics from the University of Massachusetts, Amherst, and she is with us today to talk about machine learning and causality. So thank you very much for coming, especially in person.
Yeah, thank you for having me. It's so good to see faces. It's been a while since I've talked in front of faces, so I'm very, very, very excited. So thank you guys for coming. Before getting into the meat of everything, I just wanted to give you an idea about who I am and how I've gotten here. A lot of the work that I have done and continue to be interested in doing looks at and develops causal inference tools to address or to guide decision making, or it develops predictive models to address real world problems. And while these are two tools that sort of can be generally used in whatever, I tend to use them in the context of healthcare. And a little bit more specifically, the last 6 years or so, I've been using them in the context of infectious diseases. So how did I get here? I want to tell you a quick story. This is a true story. My first ever project, I was working at Brigham and Women's Hospital, and we wanted to use Medicare claims to build a model that will predict mortality. So I figured, easy, I will take the Medicare claims, I will throw them into a really cool machine learning algorithm, and the machine learning cog will fuel the healthcare cog, and greatness awaits for me. The problem is, or not the problem, something that I noticed that was weird is that I realized that my models are saying or suggesting that hypertension is protective. So hypertension is good for you. If you have hypertension, you're less likely to die. And you don't really need to be a physician to realize that doesn't make a whole lot of sense. But you know what? The accuracy of my model was great. So I had no qualms with this, moved on. And then one day I used my model, or the model that I developed, I used it to predict mortality on a slightly less sick population. And immediately the accuracy of my model deteriorated completely. This, what I just described, is an example of something that we refer to as distribution shift. And we'll get to what distribution shift is in a little bit more detail down the line. But the thing that was missing here is that something was off in our machine learning model. And what was happening here is that when the hospital was coding the patient's stays, when they were filling out these claims, they had a limited number of slots where they can write the patient's main ailments. So for patients who are super sick, who died within 30 days of discharge, their slots were filled with really terrible things like cancer, stroke, dementia, all these super intense things. But for milder patients, they had enough room on their charts so that you can put in hypertension in there. So what ended up happening is that hypertension was associated with less severe outcomes. So what this model that I developed was doing, it was picking up on spurious correlations that existed only in this data set. And that's why when it was applied in a different data set, it didn't generalize well. So what was missing here in this machine learning model is the fact that the model did not incorporate some causal knowledge that we know to be true about human physiology. That is, hypertension is not good for you, does not causally reduce your likelihood of death. So that was one big idea that I learned at the very beginning of my research career, that predictive models that incorporate something about causality tend to be more robust to distribution shifts. So that's idea number one. The second idea has to do with intervention assessment. Intervention assessment is different from predictive modeling in that we're not trying to find out what is the most likely associated outcome with a specific set of characteristics. Instead, we're trying to build a system that guides a physician, for example, and tells them, okay, what is the effect of a specific intervention on your patient? So what do we do? How do we build these kinds of systems? What do we do with our observed data? My argument today will be that we need to build causal models in these settings. And I will let underappreciated scholar and 5-time MVP Steph Curry tell you why.
It's a game changer. But will it make you better at basketball? We decided to put it to the test. You ready? It's got to be the dry spray.
So you can imagine the kind of frustration that comes with going out, buying Degrees dry spray and expecting that, oh my gosh, I'm gonna shoot 3-pointers like Curry. And then you realize, no, it's not causally making me better at basketball. And we'll get in a little bit into the details of like how causal models are different from predictive models, but for now, trust me that they are the same. Now, in a healthcare setting, we risk way more than just frustration. We risk catastrophic events if we depend on these associative models rather than causal models. So we really need to use this data to build causal models. And again, it's easy to think that, okay, I'm going to use causal models. Causal models are going to, or the causal cog is going to fuel my healthcare cog and greatness awaits for me. Again, something is missing. And this thing here is that causal models traditionally assume that there's an abundance of data. There's lots and lots of data that are available to train our causal models. And that is typically violated, especially in healthcare settings, and especially in resource-constrained healthcare settings, where we don't have the money or the ability to collect more data about more patients. The great news is that the machine learning community has thought a lot about this question, and we've developed what I will refer to continuously as efficient models. By that, I mean these are models that are trained to deal with limited and small samples, so they're efficient in that they make the best use out of the available data. So if you have heard the term statistical efficiency, that is what I'm referring to, not computational efficiency. So yeah, machine learning has thought about this problem a lot. And this brings me to the second big idea that I have, which is that we can use machine learning methods or machine learning tools to make causal inference more efficient. Okay, so today I'll be talking about 2 projects where I use those 2 ideas. Jumping right into the first one, this was not the required reading, this was the other one. We're going to first look at some work that I've done where we've used ideas from machine learning to make causal inference a little bit more efficient. In this work, we want to study how do we build models that enable or guide decision making. Consider an example like the illustration that's on the slide. We want, or this physician wants to decide whether or not to administer a certain treatment to her patient. And this treatment may or may not extend the patient's life. What she really wants to know is what is the outcome of her patient if her patient gets assigned the treatment, or if her patient doesn't get the treatment. And we refer to these outcomes as the counterfactual or potential outcomes. And we'll use capital Ys to denote them with a subscript that denotes the specific treatment assignment. And this paradigm is usually referred to as the Neyman-Rubin potential outcomes framework. If you're familiar with causal inference literature, this is one of 2 big causality schools. Now, I said something earlier about causal models being different from predictive models, and I said I would talk about it in a little bit later, and this is it. The reason why causal models are different from predictive models is that potential outcomes are not the same as observed outcomes. Potential outcomes, we can only observe one or the other. You will never get a data set where you observe every individual in the data set has been assigned both the treatment and the non-treatment arm. And that's a missing data problem. We'll never observe both. We'll only get to observe one. And that is what we refer to as the fundamental problem of causal inference. Now, if the data that you're using to learn your causal model is coming from a randomized controlled trial, you have a data missing at random problem. But if you're using observational data from electronic health records, for example, from a hospital, then that means that the treatment assignment was biased at training time or in the data that you observed. So for example, sicker patients are more likely to get the treatment. Your treatment assignment is not random. And that is a problem of data missing not at random. And it's a little bit more complicated. So what have people done to sort of address this causal problem? When faced with this kind of challenge, people found that there are 3 assumptions that, if satisfied in the data, allow us to identify and estimate the potential outcomes despite the fundamental problem of causal inference. I won't get into the details of these assumptions, but their names, in case they ring any bells for anybody, are strong ignorability, sometimes referred to as no hidden confounders, overlap or positivity, and consistency. I'm happy to go into the details of these if someone's really interested, but they won't matter a lot for our conversation. Now, if those 3 assumptions are satisfied in the data that we have, then we can use specific statistical tools that manipulate the data in a way that makes it kind of look like it came from a randomized control trial. And if you've heard of inverse propensity score weighting, then that's one of those tools. If you have not heard of it, don't worry about it. So given those 3 assumptions, what typically happens is that people try to estimate the potential outcomes to the best of their ability. So they say, okay, let me try to find the best possible, the most accurate possible estimate of those 2 potential outcomes. And for the rest of the talk, I will be using a subscript 1 to denote the outcome under treatment, and subscript 0 to denote the outcome under non-treatment. So as I mentioned, the usual goal becomes, let me try to estimate these 2 values to the best of their ability, to the best of my ability. Okay, what we were thinking when we started this work is, okay, we know that we need causal estimates to guide good decision-making. But do they have to be exact causal estimate? Do we have to go for the most accurate possible estimate? I see some shaking of the heads, which I agree with. In situations like I just outlined, asking a model to give us the most accurate possible estimate is kind of like asking a model to give us statements like this. The treatment will increase life expectancy by 6 years, 4 years, 6 months, 11 days, and 2 hours. And as some of you might guess, this is like a comically an overkill, right? Instead, it is often sufficient to say that the treatment will increase life expectancy by something like 4 to 5 years. So in this paper, what we did is we sought to build models that will help us or enable us to make statements such as the following. If treated, the patient's life expectancy will be 80 to 85 years. If not treated, it will be 70 to 75 years. Let's break the statement down a little bit to try to get a concrete learning or estimation objective. The first thing is that we have every patient is represented by a set of characteristics X. So these are like patient age, gender, like things like that, income, status, past medical history, all that. And we want to make inferences about his or her life expectancy. So we want to say that their life expectancy under the treatment will be 80 to 85 years. Now this value 80, it will be the output of a learned function f, and we will use subscript 1 to denote treatment assignment is equal to 1, and the superscript L to denote that it is a lower bound. We also want to learn a similar function that is the upper bound of that value of that life expectancy under treatment, and also we want to learn the analogous functions for the outcomes under non-treatment. How are we going to learn or estimate these functions? The first thing that we're going to do is we're going to make the set of usual assumptions. These are the 3 assumptions that we talked very, very briefly about. But the usual assumptions don't really solve our problem, because if we do the thing that we typically do in machine learning, which is let's minimize the mean squared error so that we get a good function, that is implicitly trying to get the most accurate possible estimate, right? And we've already established that that's an overkill. So what we're going to do instead is we're going to require that those 4 functions correctly cover the potential outcomes. In other words, the potential outcome is almost never lower than the lower bound or higher than the upper bound. And our metric of interest here will be to achieve a low false coverage rate, meaning that the probability of observing a patient whose potential outcome does not lie within this interval that we've estimated is very, very small, specifically less than a pre-specified tolerance parameter rho. And our final learning goal will be to learn meaningful upper and lower bounds such that the false coverage rate does not exceed rho. I will strategically set aside for a couple of slides what it means to have a meaningful bound. We will focus on the false coverage rate, and then we'll get to the meaningful part in a couple of slides. Okay, I just presented to you two goals. One tries to get the most accurate possible estimate, and the other one, which is our suggested approach, it tries to get meaningful bounds that do not violate this required false coverage rate. How do you know which one is better? One way to compare the two is by looking at, or by trying to say something about how they perform on data we have not seen. And this is the part where machine learning comes in, because in machine learning, we've developed a lot of really good tools and analysis techniques that kind of theorize about how the model will behave on data we have not seen. Specifically, we want to say something about the error that we will have on unseen data. And I will use an R with a subscript F to denote the risk of a specific function F on unseen data. And this usually is referred to as the generalization error. Ideally, we want to say the generalization error will be equal to something. But the problem is we will never observe this unseen data. By definition, it is unseen data. So we'll never be able to empirically estimate this risk. So what are we gonna do? What we usually do is we say, okay, with high probability, my error on unseen data will be less than something. And we want this something to be as small as possible, because that means that we have low error on unseen data. Now, for the usual objective that tries to estimate the most accurate possible estimate, this something depends on the training data error. So if we have a lot of error on at training time, we also have a lot of error on test time. It also depends on the true function complexity. What is a true function complexity? It is sort of an abstract idea that we can measure using things like, if you've heard of VC dimensions, Rademacher complexity, covering numbers. If you've never heard of any of these, that is totally fine. You can think of it intuitively as a way to quantify the idea that linear functions are likely easier to learn than slightly nonlinear functions, which are easier to learn than very nonlinear functions. So the other thing that our generalization error bound for the usual objective depends on is n, which is the number of samples that we have at training time. So if you have a very, very complex function space, your true hope of getting good generalization error depends on how much data you have. So more data, you're good. Less data, you're not so good. And the problem in healthcare is that a lot of the functions that we try to estimate are actually truly complex. So we end up in a place where we really need a whole lot of data to like get a good estimate of the function, which again is a problem in resource constraint settings. So how does our approach compare to this? One like big question that we wanted to answer is, can we avoid this dependence on the true function class, the complexity of the true function class? So can we reach the setting where the true function class doesn't super matter? And the big thing that our work answers is that yes, we can do that. We can get around that if all we need are bounds rather than the most accurate possible estimate. In the next couple of slides, I will tell you how we were able to, or like an idea of how we were able to avoid this dependence on the true function class. If you're not interested in like an intuition behind the theory, you can zone out for the next couple of slides. I encourage you not to, because I think it's cool, but hey, to each his own. On a very intuitive level, our theory suggests that in most cases, estimating an upper and lower bound on the potential outcome is easier than estimating the true potential outcome. So the illustration on this slide, we have on the x-axis something like patient age, and this dotted black line shows the true function, and the shaded region around it is the noise. So you see that the function itself is like kind of nonlinear, but you're able to perfectly cover it, perfectly bound it up above and below by simple linear functions. So that's the core intuition in our work. Now, because the arguments are completely symmetrical with respect to the upper and lower bounds, I'll just look at the lower bounds. So we'll talk in a bit more detail that how hard it is to get a lower bound that covers the data correctly. So the top part of the slide shows the generalization risk, which we denote by R. It is defined as the probability of observing a patient outside of the training data, such that the estimated lower bound is higher than the true counterfactual or true potential outcomes. Now, let's say that we want to be extra cautious, and not only do we want this lower bound to correctly bound the data, we want it to bound the data with some buffer or margin region. And this margin parameter we will call gamma. And that will play an important role in our theory. You can intuitively think about this gamma as a measure of confidence. The more buffer I have, the more confident I am that I won't observe any data points that are not covered, or that I've correctly lower bounded the data. And we will redefine the generalization risk to include this gamma parameter. Now, if at training time, there are some data points that are violated, so they're not correctly bounded, like here you see them, they're falling outside or underneath the lower bound, we refer to the differences between each one of those points and the estimated lower bound as violations or magnitude of violations. That will become important later. Okay, so the slightly scarier slide, but still interesting, I promise you. What we find is that for every value of this gamma, this confidence parameter, and for a training data set of size n, with high probability, we have that our risk or unobserved risk is bounded above by this monstrous term. We'll go through it. If you've looked at generalization error bounds before in your life, this first part is sort of like not that different from what you've seen before. The slightly different part is this second part. And this second part shows up when we are trying to learn causal estimates from biased data. And it's appearing because we're making estimates for the general population based on a biased sample. And a little bit more specifically, this first term measures how different the general population is from the population that received treatment assignment T. So if you have very, very biased treatment assignment, so only super sick people get the treatment, this term is going to be really, really big. In randomized control, if your data is coming from a randomized control trial, this term will go to 0, and this entire giant term under the square root also goes to 0. But to really see or to get to the core of why it makes more sense to estimate bounds rather than the most accurate possible estimate, it'll be interesting to look at this term K. K breaks down into 2 terms. The first one measures the complexity of the function, and here it depends on gamma. Remember that if we were going after the usual term, the function complexity depends on the true function complexity, like what the true function looks like. Whereas here, it is controlled by gamma, and the larger the gamma is, the smaller the complexity is. So that's a good thing. The second term is the violations, and it's also controlled by gamma. The larger the gamma is, the smaller the violations are. If I've completely lost you for the last couple of slides, the only important takeaway here is that the generalization risk is controlled by this margin parameter gamma and does not depend on the true complexity of the function space. That's a win. We were able to avoid the dependence on the function complexity or on the true function complexity. Okay, cool. The next part is interactive, so yay. We can go back to something that I previously set aside, which is what does it mean to have meaningful bounds? For example, the 2 sets of bounds that you see on the slides, they perfectly cover the data. How many people think that bounds A are better? 1, 2, okay. Got some takers, good. How many people think that bounds B are better? Nice, okay. I missed doing this in person. So this is great. Thank you guys for participating. The reality is that this is a trick question. The optimal estimates can vary on, so you all were right, so good. The optimal estimates can vary based on an application by application basis. So for example, the bounds in A give the tightest intervals on average, but you'll notice that for younger people, they're a little bit wider compared to older people. Whereas the bounds in B, they make sure that no subgroup gets too wide of an interval. So they minimize the worst case scenario. And you can think of these as more fair or equitable bounds. And ideally, we want an approach that incorporates both kinds of bounds, or both kinds of, not just both, these and many more possible objectives or utility functions. So this brings us to our suggested approach that I will present at a high level of abstraction, but if you are interested to find out what are you actually optimizing, please ask. I'm happy to get into the details. What our approach does is it maximizes some utility functions or some specific utility function defined by the end user, such that, or while imposing the required false coverage rate as a constraint. So we can plug in different utility functions in here in this, like instead of this, and we can, for example, like replace this utility function with, I want to make sure that the worst case scenario is never too wide, so minimize the maximum interval width. Or we can do something like, I want on average the intervals to be as tight as possible. In that case, we would minimize the square differences between the upper and lower bounds as weighted by this WI. Not that important, but it is the inverse propensity score, which again manipulates the data in a way to make it look like it came from a randomized controlled trial. So for example, upweights people who are very, very like unlikely to receive the treatment, or downweights people who are very, very like common. If you're familiar with reinforcement learning, this is kind of like importance sampling, or the importance weights in reinforcement learning. In our paper, we also show that when you use the absolute rather than the squared differences, you end up with something like the quantile regression. From here on out, I'll sort of assume that we'll define the utility to be, we want the tightest intervals on average, because there are more baselines that are interesting here. But before jumping into baselines and empirical results, I wanted to stop to ask, when does our approach outperform others? It turns out that what other approaches do is that they try to estimate the function to the best of their ability, and then they shift it up and down by some value. And this is what they expect to get. But in reality, what happens is you typically don't have enough data to sort of estimate the function with such high precision or high accuracy. So you end up with an estimate that looks like this. And then you shift it up and down, and you get some violations. So our approach outperforms others when we don't have enough samples to sort of like perfectly or accurately estimate the true function. There's another big reason why our approach does better, which is the baselines have to make a decision about what is a good shift. So which one of those two shifts are better? We don't know. So when the baselines are deciding how to shift this estimated function up and down, they're implicitly making assumptions about the residual or noise distribution. So another advantage of our approach over baselines is that we don't make such assumptions. So our approach is more robust when these assumptions are violated. There are many such assumptions on the residual distribution, but the one that I think is violated a lot in practice is the assumption of well-behaved residuals. What does it mean to have well-behaved residuals? It means that there's a central value, and all the noise or residual values tightly cluster around the central value. So for example, the noise has mean 0 and standard deviation something. And this is violated when there's heteroscedasticity, which means that the dispersion of the noise is not uniform across, in this example, across age. Okay, now let's pause for a second to take a sip of water. Is it okay to take questions?
Absolutely.
Okay. Oh, wow, I didn't know that. You can ask away.
Yeah.
Go ahead.
So although everything is non-parametric, so are there any correlation between the bounds with the confidence interval?
Ooh, yes. Yeah, we'll get to that. We'll get to that, and it's one of the baselines that we talk about. Our estimator is non-parametric. I didn't mention that because I didn't show you explicitly what we're optimizing, but we will use kernel regression based models. So both our model it is non-parametric. Go ahead.
And also another question that since it seems that when the sample size increase, your method gonna be kind of underperformance compared to other methods since there are more and more information. So are there strategies how to
Yeah.
take the N since it depends on the complexity of the real function actually.
Yeah.
So how to decide that number?
Yeah, that's a really, really good point. This is actually something that this is an intuition that I have that I've seen empirically, but I don't have any like theory to back it up. I think our approach asymptotically converges to the mean squared error estimator when the data gets bigger and bigger and bigger. So get closer and closer and closer to the actual. So I think this is again based on like empirical evidence that I'm like seeing as I'm running things. It would be very interesting to write that paper to like show that we actually converge to something that's super tight, if not the mean squared error. I see something on the chat. Is that a question? Should I be? Because while we figure that out. Questions? Yes.
So you use two linear functions for the upper and lower bound.
Mhm.
So like, would that be the case that those two linear functions intersect?
Oh, it's a good question. We explicitly put it in. I'll show you this real quick. I don't want to. So I stopped at slide 34. Okay, I'll show you this because this is in the additional slides. Let's see, where is it? Yes. So we do have this constraint that sort of asks for the lower bound to always be less than the upper bound. But one other thing that I'll say real quick here is that we do not pre-specify the functions to be linear. We actually pick the shape of the function based on cross-validation. So the cross-validation algorithm, roughly speaking, picks the simplest function that correctly bounds the data or correctly covers the data. So we don't a priori say it's linear. So yeah, that's one version of what we're optimizing. Okay, I am going to, any other burning questions? Okay, never mind. Okay, cool, moving on. All right, because of the fundamental problem of causal inference, we don't have access to the ground truth. Like we don't have a target label because we're missing 50% of the labels for everybody. So it is notoriously difficult to sort of evaluate causal models. And for this reason, we, along with a lot of other authors, typically use semi-simulated data, where we extract the input data, such as patient characteristics, from real data. So it has like the nice hard messiness of real data. And here we extracted the input data, the X features, from randomized controlled trial data called the International Stroke Trial. And then we simulated the outcome. And this makes it easier to evaluate because now that we've simulated the potential outcomes, we actually have the ground truth. And we also introduced here confounding because the data that we're using comes from a randomized controlled trial, so it doesn't have confounding. Okay. And the way we did that is we downsampled older folks who do not get the treatment to sort of mimic a situation where the older you are, the more likely you are to get the treatment. As for our baselines, the first one is a Gaussian process with confidence intervals. The problem with confidence intervals, I found this very interesting because I did not know this before starting this project. They don't do well at all in small samples. And there is a number of, like these papers are cited in the paper that you guys have for this reading. It's well documented that when you have small samples, confidence intervals don't really do well because they make such restrictive assumptions about how the distribution of the error. So you're assuming that the distribution is like Gaussian and has this mean and has this standard deviation. Say that again.
It only work with asymptotic.
Yeah, exactly. That's exactly true. All the guarantees that we have on confidence intervals is that asymptotically they work. We're never in asymptopia. So like in finite samples, it doesn't really work. So first baseline that we'll look at is a kernel regression, really not really a Gaussian process, but same thing with classical confidence intervals. The second set of baselines that we will look at is a kernel regression with conformal intervals. Conformal intervals are a little bit better than confidence intervals because they don't make such strict assumptions about the distribution of the data or the distribution of the noise. So they tend to perform a little bit better in finite samples. And for all the models, including ours, we will use like kernel-based methods. Even Gaussian processes are kernel-based. And here we will use a polynomial kernel of second order. And we set the false coverage rate, or the required false coverage rate, to be 0.01. So anytime one of the baselines gives us a false coverage rate that is larger than 0.01, we're going to be unhappy with it, and we're going to say this violated our required false coverage rate. Okay, let's look at results. On the x-axis, we will have the H, and on the y-axis, we have the outcome under some treatment assignment. And we're going to look at the achieved false coverage rate, so the false coverage rate that is achieved by each one of the models. And we're also going to look at the mean interval width. So smaller mean interval width is better. And again, false coverage rate, always want it to be less than 0.01. We simulated a heteroscedastic setting to really highlight the advantages of our model. So the black dots that you're seeing, this is the data at test time. So this is not the data that we used to train on. This is the data that we're testing on. So it's outcomes for the test set. The first baseline is the Gaussian process with classical confidence intervals. And we see that it is violating the required false coverage rate by quite a bit. So we asked for 0.01. It gave us 6.5 times what we asked for. So that's no good. The kernel regression does not violate the required false coverage rate, which is good, but we'll see in a second that it misses an opportunity to create tighter intervals, because it sort of assumes that the intervals are constant width. Like you see that, like this is just as wide as this, just as wide as that. So it sort of misses a good opportunity for tighter intervals. And this is our approach, which gives the tightest mean interval width, so good, lower is better, without violating the required false coverage rate. So yay, we win. There are more results in the paper if you're interested in, this is like a one-dimensional setting. There are more complicated settings in the paper. So to sum up this first part, we showed that estimating intervals is often easier than estimating the sort of most accurate possible estimate of the potential outcomes. And we proposed an approach to find meaningful bounds without violating the required false coverage rate. I've shown you both theoretically and empirically why it would outperform the baselines. I'm going to stop quickly for maybe one more question, and then we'll move to something new. Clean slate. So if I've completely lost you, new stuff. Yes, go ahead.
How do you view when decision makers specifically ask for like point estimates?
Oh,
in
yeah.
my experience, they usually use the point estimates for their own like models or.
Oh, interesting. Yeah, it's a good question. This is not like this kind of set of tools would not answer that kind of question. Like if they're explicitly asking for a point estimate, then giving them bounds might not be. Like it might just be better to go for the models that estimate the most accurate possible estimate. If you really needed to, for some reason that I can't quite think of, if you really needed to use this in the context of someone who wants like point estimate, then you would take the midpoint or something like that. Like estimate the upper and lower bound and take the midpoint between the two. It seems so roundabout. So I don't think this would get at that kind of question. But yeah. All right. So new stuff. This is the paper that I think it was a required reading. So this is work where we use this idea that machine learning models would be more robust if we incorporate something from causality or causal ideas, and specifically robust against distribution shift. What is this distribution shift we talk about? Distribution shift refers to this phenomenon that the data at training time is different from the data at test time, or the distributions of the two data sets are different in some way or another. And what I'm going to talk about is distribution shift in the context of infectious diseases. And this is work, I explicitly state that because it started before COVID. So this is work that started in 2017, 2018. And the last paper was a paper in ICML in 2021, which is the International Conference on Machine Learning. So in this set of projects, our aim was to build models that take in information about the patient and predict the likelihood that this patient will get infected with a contagious disease. And here, the training distribution is different from the testing distribution because of asymptomatic carriers. I think in this day and age, we all know what asymptomatic carriers are, and they are patients who carry the pathogen and spread it without displaying the symptoms, so they're less likely to get tested. I always had to like spend 3 minutes explaining what that is back in 2018 or something. So unfortunately, everybody now knows what that means. But the one thing that I wanted to point out quickly is that the problem of asymptomatic carriers is not at all unique to COVID. The first asymptomatic carrier, it's almost ubiquitous to like a lot of infectious diseases. The first asymptomatic carrier that was ever identified was, her name was Mary Mallon, and she was carrying typhoid pathogen and spreading it around without displaying symptoms. This was in the 1930s, and then people called her Typhoid Mary. So how does this relate to distribution shift? The issue of asymptomatic carriers means that if this is our full distribution, we have some infected patients and their label Y is 1, and we have some uninfected patients and they have their label Y is equal to 0, but only some of the infected patients display symptoms, whereas for the sake of simplicity, let's say that uninfected patients have no symptoms. During training time, because symptomatic patients are far more likely to get tested, so we have a lot of their data in our data sets. So they're very overrepresented in data sets, whereas the other two populations are undersampled. But at test time, we want to apply this model to the full population, and we want to correctly pick up on asymptomatic carriers and differentiate them from the healthy individuals. And what usually happens if we're not careful is that we'd be able to pick up on symptomatic infections, but not asymptomatic carriers. And there are a number of reasons why this could happen, but I wanted to focus on one of the reasons which happens because of the way that we train our models. So the typical machine learning pipeline sort of goes as follows. We have data and we define a function class. So for example, it can be the set of all linear functions or all linear models. And then we specify an algorithm where we put the two, the data and the set of function class. And crucially, this algorithm typically will look at the validation set or the performance on a validation set and pick the model that performs best on the validation set. And that one will become our final model. In the day and age of deep neural networks, we no longer operate in this simple linear function class, and we're now looking at a giant set of sort of neural networks. And what we see is that a lot of models, or a number of models, perform well on this validation set. So how do we pick from these? And this is a case of what I'll refer to as underspecification. In words, underspecification means that the held out data set does not uniquely identify or specify a good model. What happens is that within the set of models that perform well, only one of them may extrapolate to unlikely data, or maybe one of them will extrapolate to unlikely data that we do not see at training time. So that's what you see here. These two models are not extrapolating well. They're not identifying the asymptomatic carrier, whereas that last one is. Did you want me to finish at 5:15? Is that what? Okay.
I think we can go a bit longer and then we can
Okay.
do questions as we go. So
Okay.
we kind of ask questions at the end and
Okay.
maybe you can stay for a few minutes for.
Okay, sounds good.
Perfect.
Okay, cool. All right, glad we clarified that because I caught the time and I was like, oh no. But anyway, powering through. So what I wanted to sort of like say is that we can use ideas from causality, or we can use some causal knowledge to somehow pick the models that generalize well under distribution shift. And we, to like state this a little bit more generally, we can use or we can regularize our function space such that the models that remain are the ones that conform to causal ideas or causally defined data generating processes. And this basically prevents our model from relying on spurious correlations at training time that may cease to exist at this time. And we're going to talk for the next couple of slides about a recipe that allows us to incorporate this causal knowledge in our training process. So we start by outlining some knowledge that we have about the data generating process in what we will call as a causal DAG, or causal directed acyclic graph. A causal DAG simply depicts the relationship between different variables that we observe, or latent variables. And here arrows denote causal relationships. So X may cause Z, may cause Y. Going back to our original function space, we're going to penalize models that do not conform to this DAG. So if you think of these three functions as functions that perform well, so these are all really good on the validation set, we're going to, only this one sort of conforms to the causal DAG that we think is correct. So we're going to penalize these. We're going to remove them from our function space and hopefully end up with the one function that both does well and generalizes or conforms to our causal DAG. In the specific example that I'm about to talk to you about, we also have access to auxiliary label, and I'll tell you what this auxiliary label or auxiliary data, and I'll tell you what this auxiliary data is in a second. It is probably possible to define like a different causal regularization scheme without auxiliary data, but this is what we have here. Let's try to follow the recipe that I outlined a second ago, and we'll start by defining a DAG for our friend Jane. So for this individual, Jane, she has a hidden or latent state that encodes her infection status, and it evolves over time points 0, 1, and 2. And this infection status is unobserved, and that's why it's sort of white, whereas everything else that is observed will be shaded gray. So this infection status is controlled by her characteristics. So for example, age and whether or not she exercises good hand hygiene. And this infection status controls her true infection state, which we will say here, this is a Y is the true infection state. We will say here that Jane got tested at time point 1. So we don't know her infection state at time point 0, but we know her infection state at time point 1 and 2 because that's when she got tested. And I'll use white nodes to denote something that's not observed and gray nodes to denote something that's observed. To make this example a little bit more interesting, we'll say that Jane tested positive at time point 1. We also have a similar DAG for her neighbors. And here, neither of the neighbors have gotten tested, so you'll see that their Ys are all not gray, they're white. And we'll also assume that we are really good at contact tracing, and that's the auxiliary data part, is that we have auxiliary data in the form of perfect contact networks. This doesn't really happen in COVID, but it happens in infectious diseases that spread inside a hospital. That's why I wanted to give that disclaimer that this is pre-COVID. So we have the contact networks, and the contact networks tell us that Jane's contacts came into contact with her at time point 1. The important part here from a causal perspective is that we know that in order to get infected, you have to have caught it from someone. So with high probability, one of Jane's 2 contacts is infected or is an asymptomatic carrier, right? So having this additional causal knowledge allows us to sort of know, you can't really tell really, but these are all shaded now, like the Ys are all shaded now, because of the causal DAG, we're now able to say we're able to like get pseudo-labels, or we're able to impute what the labels for Jane's neighbors are. With high probability, one of them has to be infected. Cool, so we have the labels. Is there a question? Someone? No. Okay, cool. Now that we have the labels will help us regularize the model or help us with model selection. How? It acts, or these labels act somewhat like data augmentation, where we're adding additional labeled examples that tell us how the model should behave on the subpopulation that typically doesn't get tested. What does that mean? If you have on the x-axis, like this is some characteristic, and the y-axis shows the probability of infection. And this interval that you see, I don't know if you can see it. Yes, this interval is the set of patients that are unlikely to get tested because they're unlikely to display symptoms. In this setting, a lot of different models can fit the observed data. So we don't really know how the model behaves on this interval that typically doesn't get tested, so we don't have their labels. But if we have their labels through pseudo labeling, then we will know, or we will define how the model should behave on this underrepresented sample. And this gives us the final objective where we iterate between two things. I'll go through this a little bit faster, and I can answer questions about details later. So what we're iterating between is two things. The first is we find the optimal pseudo labels for all untested individuals in our data set. And then in the second step, or given those pseudo labels, we now find the best predictive model F that tells us the probability of getting infected given those imputed label. I'm going to jump through this because we don't super have the time. Okay. The problem here when we're trying to evaluate our model is kind of similar to the causal setting in that we don't have access to the asymptomatic labels during training time because they're by definition not identified by the systems, they're not tested. So again, we sort of looked at simulated experiments. We simulated a universe with three types of people. First is symptomatic if infected, and these are patients who, when they are exposed, they get infected and they display symptoms, so they go get tested. So they are more likely to be identified by the hospital system as, oh, these are infections. And the second group of people is asymptomatic if infected. These are individuals who become infected, but they don't display symptoms, they're asymptomatic, and they almost never get identified by the hospital system. And the third group of people, you can think of these as people who wear their face masks, wash their hands, and they're very unlikely to get infected even if they are exposed. And then we connected people, we drew, in our simulation, we drew networks from a stochastic block model. If you don't know what that is, that's not super important. It is just a way to create networks between people that allows for a nice community structure. So to test the empirical performance of our model, we simulate training data with varying levels of testing odds or testing likelihood of testing. So on the, let's see, this is the right side. On the right side, yes, on the right side we have, this is so weird. On the right hand side we have almost randomized testing, and on the left hand side we have very biased testing where symptomatic patients are far more likely to get tested than asymptomatic patients. And on the y-axis, we will look at the AUROC, which tells us how good we are at predictions on the test set. I'll present two benchmarks, but there are more in the paper. The optimistic model, it sort of assumes that all infections or all asymptomatic carriers have been identified by the system or have been tested. The no exposure model sort of completely ignores exposure and tries to predict the infection status based on the patient characteristics, and ours, which is the red one. And of course, otherwise we wouldn't be here. Our model does better than the baselines at every level of testing bias.
I'm wondering why the bond seems to increase a lot.
Yeah, that's a good question, because here the number of tested patients who are not symptomatic is very, very, very small. So you're trying to generalize from a very, very, very small sample. So then you get like very high uncertainty. This is a little bit sticky. Okay, cool. So the last thing that I will show you here is some experiments on real data settings. And the task here is we wanted to predict who is going to get a disease called Clostridium difficile or Clostridioides difficile infections in the population of the Massachusetts General Hospital. So this is, again, this is a hospital-associated infection. It, roughly speaking, starts and ends in the hospital. So that's why, like, contact tracing is a lot easier in a hospital setting compared to like in the wild, like COVID. C. diff or CDI is a bacteria. It's a bacteria that affects the gut, and it causes really bad diarrhea. It causes inflammation of the colon, and in very, very bad or very severe cases, it causes death. So and C. diff is also like, you can be an asymptomatic carrier of C. diff. In fact, like roughly 20% of the general population is colonized with C. diff. In this real data task, what we did is we extracted, so yeah, we want to predict who is going to get C. diff in this hospital population. We extracted data from electronic health records. So we have like patient characteristics, medical history, some demographics and things like that. And we use this data to predict C. diff or not in this hospitalization. And we constructed contact networks based on room and nurse sharing. So if 2 patients shared a room or if 2 patients shared a nurse, then they have an edge between them. Now, of course, here we don't have ground truth who is asymptomatic carrier or not, but we use this trick to create a proxy label for who is an asymptomatic carrier. What did we do? The way that you get tested for C. diff is first they test for the toxin. So they see if the toxin that the bacteria generates is in your gut. And if the result from the toxin test comes back inconclusive, they do this more sensitive PCR test where they look for the bacteria itself, not just its toxins. So if the toxin test is inconclusive, you go to PCR. And the general consensus among our medical collaborators and the medical literature is that people who test positive through the PCR test are the milder, less symptomatic patients, because you really need the toxin to display symptoms. So if you don't really have the toxin, then you're likely not very symptomatic. So we used this as a proxy for asymptomatic carriers, in that everybody who tested positive through the PCR, we kind of assume that that person is an asymptomatic carrier. So at training time, we hid all the PCR results from the models. So none of the models, like the patients who tested the PCR or who had the PCR test, looked like they were untested for our models. We hid these results. But then at test time or evaluation time, we asked the models to predict everybody, whether they were tested through PCR or through the toxin test. So that kind of creates an asymptomatic carrier proxy. And what I'm showing you here are the results from 2 metrics. The first is the AUROC, which again shows us how good we are at prediction. But then the second metric is the true positive rate at a false positive rate of 0.1. And this is the one that I like better because it's a little bit more interpretable. What we found out is that our approach is able to identify about 15% more of the C. diff cases when we fix the false positive rate to be 0.1. Real quick, the reason why I like that metric a little bit better is because it means something to our medical collaborators. They don't want a model that will cry wolf whenever there's like a tiny little evidence that maybe this patient has C. diff. So they want something that doesn't give a high false positive rate. So that's why I think that's a cooler metric to look at. Okay, so to sum up this last part, I showed you really quickly how we can use knowledge of the causal DAG to make machine learning models more robust. And I've showed you an application, which is prediction of contagious infections. This work was done with an army of collaborators that I would be remiss to not thank them. And thank you for listening.
It was wonderful. Packed.
I'm sorry.
So, no, there's like lots and lots of good stuff. And I think one of the things that's great about these talks is that it does leave us with questions. So good topics for students to explore, questions for students to ask. So what I'm going to suggest, I know some of you have another class on Central. Let's take one question and then maybe you could stick around for a few more minutes if anyone just wants to come up front. But if anyone has a burning question before they leave, I want to be respectful of that. Okay, good.
I've confused everybody. Great.
And Stephanie, are you checking the chat? We're good. Okay, perfect. So again, thank you very much, Maggie, and we look forward to having you engaging with us throughout your new time here at Michigan. Yes. So thank you.